There's a lot of including organic, hybrid, organic, inorganic, and also perovskite solar cell. Okay, and most of them are initially. Okay, I would say the original organic solar cell is relative to result from the dye-sensitive solar cell. Okay, so that's why I take this example in our chapter. Okay, in our chapter. If you look at about organic solar cell or perovskite solar cell, the concept is quite similar. Okay, concept is quite similar, but just using different p-type and n-type. Okay, and why I chose I select this topic because of this is mostly talk about nanotechnology. So for the previously solar cell is a photovoltaic, which is the bulk, but here is using totally nano powder, nanotechnology, or some of the organic dye. Okay, organic dye. Okay. So first, I will talk about the forecast. Okay, for the solar module. Okay, and also such advantage of the solar cell compared to the previous chapter of the silicon solar cell, and regarding the working mechanism and also recombination process. This recombination process also has a relative to fear factor. Okay, the higher recombination, the lower fear factor. Okay, so why I talk about the nanotechnology? Why the nanotechnology can be used as a photo generation? I would say the electron hole pair separation. What is the benefit? I would say what is the benefit for nanotechnology? Okay, this is quite simple. Okay, if you look at about the lead, right? Here is the lead. What the functionality for the lead? Absorb the light, right? And convert the chemical conversion, right? Produce the oxygen, right? Produce the oxygen. Absorb the light, right? So this is a chemical reaction, just like a small battery, just like a small battery. So if you treat each lead, okay, as a cell, right? As a cell. And then a large amount of, just a large amount of lead, which means that you can produce a large amount of the chemical conversion, right? Chemical reaction. So we call this as a photovoltaic. We call this as also a photovoltaic. Photosynthesis. This is a photosynthesis, and then photovoltaic. Just similar, but there's a difference. Okay, so for example, this is N, right? This is N. This N can carry a lead, right? So an end, if you have the end on the skin of your surface, right? Easy to just remove, right? But if you have a building, right? A building of the end attack to you, right? You will get, right? You have the big problem, right? So that means that interfacial engineering is a so-called very important. So right here we are talking about the interface engineering, right? Dye-sensitive solar cell, which means that if we can have a small nanoparticle, okay, and this small nanoparticle can be less than maybe 50 nanometer, 20 nanometer, and each particle can photo-generate electron hole pair separation. So if we can do some preparation, well preparation, to get the good current corrector, and we can convert the high efficiency of the photovoltaic, okay, of the solar cell. And also, in previously, we didn't talk about a tandem structure here. You can see tandem. Tandem, you know the tandem. Tandem, so-called a multi-junction. Doesn't mean a layer by layer, layer by layer, right? In the silicon, we couldn't do the tandem junction, right? You couldn't do it. It is a bulk. You cannot pack it to multi-junction, right? Because if you pack a multi-junction, you only have the top surface as a functionality. On the bottom surface, you don't have the functionality, right? But for the tandem structure, because you can deposit a layer by layer, layer by layer, right? So it looks like a thin solar cell. So therefore, we can create a multi-junction of the solar cell. So-called on the top junction is a cell 1, middle junction is a cell 2, and the bottom junction is a cell 3, and which can absorb the different wavelengths of the light radiation, right? So this is an advantage, okay? Is an advantage. So here is a mechanism. Later I will talk about this mechanism. But the more interesting is you can prepare. You can see here is a different color. You have a green color. You have the like a red color, right? You have different color, right? This is relative to the dark, okay? Because the major species of the solar cell for dye-sensitized is actually looks like a sandwich structure. You have the SNO2 coating glass, so-called ITO, and here is another ITO deposit palladium, PT. So you have the sandwich, and then inside deposit nanoparticle of titanium dioxide, crystalline titanium dioxide, and then inside field electrolytes, okay, electrolytes. And then still have another very important is the dark here. Dark here is dark. Okay. Later I will show you how to perceive the charge transfer. Okay, charge transfer. So this is the electron. Okay, electron. So the first step you could see here. Light assault. Electron hole pair separation, electron diffuse through the nanoparticle, in conduction band, okay? TL2 conduction band, okay? So you may ask me, are you sure the electron is transferred in the conduction band of the TL2? Yeah. Yeah, later I will show you the mechanism because this dye is a special design just meet the homo band, the normal band, sorry, the normal band is just quite meet to the conduction band of the TL2. So therefore you can transfer to the conduction band of TL2. Later I will show you. So once the electron transfer to the conduction band of TL2 and then through this external circuit, and then to here. Electron transfer to here. Okay? Electron will transfer to the dye. Okay? Electrolytes. Sorry. Electron will transfer to the electrolytes. Okay? And then this electrolytes will deliver the electron to the dye. Okay? This is step by step. Okay, step by step. And then it is quite interesting, like the dye, we can design different color. Because you have different wavelengths, right? So you have today, okay, I am, well, for example, Friday you are happy, you can design like a green color. Like Monday you are sad because you have a lot of clothes you need to take. So you using the blue color. So anyway, you have a lot of different color can select. So for the building integrated photovoltaic, you know, building integrated, building. What we call the BIPV, building integrated photovoltaic. integrated photovoltaic is quite important, like because if you have the building looks like that, okay, and then usually people say for the silicon solar cell usually is like a blue color, right? So blue color is not good because blue color it looks like not happy. Right? So you can integrate some of the solar cell. You can use in a different color, so you can have a fancy, more fancy building, something like that. Demonstration, okay? Because dye you can design different wavelengths, so therefore it shows there's a different absorption, okay? Different absorption edge. All right. So again, this is compared to difference in organic solar cell. We have different wavelengths. Okay, you have different wavelengths. And for the dye solar cell, we can design. For example, let's show you. Here, 19 page, okay? This is absorption edge, okay? Absorption edge, this is dye absorption edge. We can base on difference, this is Ruthenian dye, okay? Later I will show you about that. You have the different wavelengths, right? So you can, actually you can extend, okay? Extend the wavelengths, absorption wavelengths, to having more absorption. Visible light absorption, okay? Visible light, because based on the traditional solar cell, the crystalline silicon, you only absorb around here, right? Crystal around here, and amorphous is around here. So it is hard to get a whole spectrum, right? It's hard to get a whole spectrum. So based on the tandem structure, we can design, for example, one dye absorption this wavelength, second dye absorption this wavelength, third dye absorption this wavelength, and then pack together, multi-junction, so you can absorb the whole wavelength, right? This is the advantage, all right? Okay, just remind, okay, just start here. Because students talk about next week we have the midterm, right? Exam, right? So what is the how to take? You can having A4, okay? A4, just A4 page, okay? Whatever you want to print out, to reduce the size, or you want to write by yourself, right? It's up to you, okay? You don't need to everything to write by yourself. You can print. Yeah, you can print. But if you can see, yeah, you can reduce. Yeah. I just wanted to